Hello everyone. In this video, we are going to continue our adventure with cleaning data. In the previous video, we looked at and cleaned and dealt with the missing value of a data set that was collected from Belgium that were the electricity consumptions. In this video, we're going to continue working on the same data set. But this time, instead of dealing with the missing values, we're going to understand the extreme points and understand why they're happening and make decisions about them. Normally, these are called outliers, but the term outliers may mean many different things. So in this example, we will look at those examples, some examples of outliers, and see what those values, what outliers could mean for these cases. So like I said, we are going to be working with the same data set. And of course, we are going to import all of our modules that we're going to be using. And pay attention, in the previous video, we reached to this point that we saved our data in clean electricity data 2017. So we're just going to pick up where we left off. So now I'm going to open or load my clean data. So I read this, and now if you remember, I have the date, time, consumption, month, day, year, weekday, hour, min, and hour min. So as we saw in the lecture, we have a couple of ways to go about detecting outliers, detecting extreme points. One of them is using box plot. So once we draw the box plot, we see that this data has some flyers. So when it comes to box plot, these points that are not a part of the main data, the whiskers and the quartiles and the median, these are separated. They are indicated as extreme points, but within the realm of box plots, we call them flyers. Flyers are not necessarily outliers, and we'll see some examples of how we could distinguish between a flyer and outlier. Another way we could go about this is using histogram. Once we draw histogram shows that there are a lot of data within 30,000 to 90,000, but there are not a lot of them. I mean, we can't see anything here, but the fact of the matter is, if there were no data points here, we wouldn't see this, empty spot here. So there are some data here that are not enough to for us to be able to visually see them in comparison with the rest of the data. So that's why we also suspect that there are some flyers after 90,000. And it's the same as box plot that we can see. This visual also helps you to really see that histogram and box plot are very similar visualization techniques, but they emphasize different things and they can be used differently. Of course, box plots are much better in terms of detecting the flyers and extreme points. Another method we could use to detect the outliers by only using one attribute or univariate way of dealing with outliers is using plus minus 3 sigma. The plus minus 3 sigma assumes that the distribution of your data follows normal distribution. We can see it is not exactly normal distribution in the histogram, but it does look like it. So we assume that, and then we say, okay, if it is a normal distribution, so there is a 99% chance of all of the data being between plus and negative 3 sigma. So we calculate the mu and the standard deviation, and then we print out the upper and lower bound. The upper bound is 91,000, and the lower bound is 17,000. We can see that there are not a lot of values on the lower bound, so we are good there. There are not a lot of flyers or extreme points here, but consistent with the histogram and the box plot, we can see that there are probably some values after 91,000. So we use these values to extract the flyers or the extreme points. So if the consumption is less than this or higher than this value, I have written the code so we can see them. So we can see all of the cases are higher than the upper bound. There is no case of the lower than the upper bound. And the way I'm understanding that, I'm just eyeballing the consumption. and all of them are greater than 91,000. So these three ways are legitimate ways to detect extreme points. But since this is not a one-dimensional data set, we have more than one dimension, it's better to actually use multivariate ways of detecting outliers. And the way we go about this to sort of add variation or add attributes in our analysis is to see if there are other attributes in our data that may influence the existence of outliers, extreme points. And one of them that makes sense for the electricity data is hour min. Based on the time of the day, the electricity demand, electricity consumption might be very different. So to be able to detect outliers in a better way, we sort of have to see if there are outliers within each of these time frames around across all the data set. So to do this, we create a box plot that each box represent one of these 48 possible 30 minutes intervals throughout a day. So we use a series. We created like an empty series, and then we go through all of the possible times, and on each of those series we sort of like put all of the values for that specific time. So once we run this, now we will see we have 48 different box plots, and we can sort of see a trend in our data because around the morning 7 a.m. There are there is a surge in demand, so that we can sort of see that, and also there is another surge in demand around 8 p.m. So now we can see that there are detectable outliers in this way of looking at the data as well. So if we look at these extreme points or these flyers here and sort of like see if they are consistent with them being too higher than their surrounding neighbors, then we will know that something must have gone wrong there. So to do this, we should be able to extract all of these flyers from the this box plot. So everything that you see here, you don't have to sort of like for example, you want to find this one, so you want to say, okay, where exactly that goes. It's around 90,000. Well, we don't really know because it's visual. We could get access to the actual values because it's a programming environment. Why not? So the way you go about this, you can say, I want to get the output of this visualization. So once we run this, instead of just showing this, it also gives us an output of this visual. So if we look at the output is a combination of things. So it has information about the whiskers, it has information about the caps. So these are the whiskers, these are the caps, and so on and so forth. And also about the boxes, about the medians, about the flyers. So we could sort of like get the exact values of all of those elements of the box plot. So for example, the whiskers, we can see, for example, the whiskers for the first box plot is from 41,000 to 47,000. So if you look at that box plot, is from 41,000 to 47,000. And the next whisker is from 63,000 to 85,000. From 63,000 to 85,000. So these are the whiskers. But what we want are the flyers. So we can go ahead and get access to the flyers. And we can see that, for example, on the third box plot, we have two flyers. If we go scroll up, you can see on the third, 1, 2, 3, 4. On the fourth one, we have two flyers. 1, 2, 3, 4. On the fourth one, we have two flyers. And then so on and so forth. So those are the other flyers that we have. So we want to get access to these in a way that we can like code them. So we create a dictionary, and for each label, we say if there are flyers. So for example, for this label, we know there are 2 flyers for this time of the day, and then for 1:30 p.m. there is 1 flyer, and so on and so forth. So to sort of get access to these values from the data, we create a function we call detector, and we apply this to our data frame. And if in that specific time, which is r.hour min for each row, that value is the same as the values that are in here, we detect that that value is actually that flyer. So we apply this function to the data, and we create a data frame called flyer df. And the flyer df basically tells us the values that could be flyers in our data. So you can see that even though there are a lot of them are at 80,000, in contrast with the other method, with the univariate methods of just using the 6 sigma, like plus 3 negative sigmas, now these 92,000 seems to be okay because they are probably in the time that there are a surge in demand. So we assume that these are the most likely candidates for outliers. There are still flyers. There are still, we don't know if there has been a mistake in inputting these values in the dataset. So to check if this is the case, let's go ahead and take a look at the 20 points before and the 20 points after that. This is a similar thing that we did for understanding missing values. So once we run this, now we see that this is a clear case of a mistake or an outlier. We can see that if it was, so like this data is like way different than the points next to it. I mean, of course, we know the way that electricity consumption increases, so it's not like a island of itself. So it's sort of like shifts within time. So because of the time series element of this data, we sort of like suspect that this is probably a mistake. And then we look at the other ones and we see that this is not an outlier at all. And probably in that day, the consumption was so high that because around this time it's probably a case of in the afternoon or something. So for example, at like 2:30, even though it's an outlier for this time, but we can see that it's not an island of itself. So the surrounding points are also showing that there must have been an extra demand in that specific day. So look at all of these other ones, and we'll see most of these are not outliers. Clearly, they are not outliers, or mistaken inputs. But we see that there's another case of outliers here. So this is another one. Flyer 25, it's a possible mistake, and also flyer 26. So all in all, there were 3 outliers, or mistaken inputs. So the way we deal with these, because they're clearly a mistake or errors in the inputs of values, we sort of assume we don't have the correct values for them. So we change them to a missing, or np.nan. So once we run this now, our data is missing. So if we look at these 3 outliers, now there are missing values. So do you remember how we dealt with the missing values, that we didn't know the values? There are abundance of information around these values. So the way we could go about this is use the immediate points to interpolate. So we do that. We see there are 3 missing values here, and we do the interpolation, and then we look at the values. We can see the missing values are inputted, and then we then check our multivariate outliers, and we'll see that now most of these values are taken care of. It was interesting that the ones that were too high off the other data were actually mistaken values. So I mean, we sort of didn't do that, but we could have sort of assumed that, these values are very similar, they're probably okay, but these looks, way far off their other data within the same category. So that's why, if you see such things, it's probably like more possible that these are mistake or outliers. So once we know that our data doesn't have any mistakes, and there are, however, some flyers within these hours, so we sort of like keep this in mind that there are some flyers in this time frame. But since they are not mistaken inputs, we are not going to do anything to them, but we are aware of their existence. In the case, in the future, having two different values for our specific visualization or for a specific algorithms, that might be problematic. Then we might have to do something about them. But as far as now, we don't do anything to these values. We just like keep them in mind that there might be something we need to do specifically for these values, but based on the specific algorithms that we will be using. So once we're done, now we save this data to the cleaned version 2 electricity data 2017. Once we run this now, we have our data cleaned, free of missing values and free of outliers and mistakes.